Okay, our next group is the Houghton Environmental Group, and they had some similar challenges at a rural location in Panama to provide water supply to a community that is underserved.
So good morning, everybody. We are Houghton Environmental Group. Today we're going to be discussing our water supply, treatment, and distribution design for Veracruz, Panama. My name is Kate Mufflin.
I'm Isabel Valencia.
I'm Lauren Cole.
And I'm Evan Rye.
So
There we go.
for a general overview of our presentation today, we're going to start with the team introduction, discussing our project sponsors, move into our project goals and the existing conditions in Peru. Then we'll talk about some design assumptions we had to make throughout our project, the design components, our cost estimate and project schedule, and then we'll end with next steps and questions and answers. So an introduction to our team, HEG's mission statement is to provide engineering design solutions for water supply, filtration, and distribution to remote and developing communities. Houghton Environmental Group develops sustainable water distribution and treatment systems, promoting water equity across the globe. So for our project sponsor was Footprint Possibilities. We specifically worked with Rick Montanari. He had a vast amount of knowledge about water distribution systems in rural communities like Peru. So he was able to provide us with a lot of valuable input that we used during our project. And if this project were to be implemented, it would be funded by Global Brigades. This is an organization that exists in Panama. So for our project goals, once again, we're an international water distribution design team in Peru, Panama. Currently, the community does not have a consistent supply of potable water. So our goal is to mitigate this concern by getting potable water to household taps. We were tasked with completing a value engineering assessment of a proposed design, which was developed in 2019 by KRV Water Solutions. This was another senior design team here at Michigan Tech. Their design utilized the local spring source in the community to get water to household taps. And in their plan, they included 2 pump houses, piping, storage, shot chlorination, and distribution. So when they received the project, their main goal was just to get water to households. And then we were given this project and asked to take their design and modify it to fit the new budget constraint, which is $40,000. And we were notified this by Footprint Possibilities. So KRV's previous design, their cost without labor was $69,000, and our goal is to reduce that. A little bit about the community of Peru. Peru is located in the Darien province of Panama. It's started on the map here. It's right along the Pan American Highway. Currently in the community, there is an existing distribution system, but it's highly unreliable. It only provides water to the community twice per week during the dry season, and this comes from a local municipality. Due to Peru's location in respect to the municipality, they receive the water so infrequently because they're at the end of the supply line. So beyond our goal of reducing the budget, our other goal is to provide a minimum of 30 liters of potable water per household per day. In the community, there is an existing spring source, which the previous senior design group utilized as their main source for water. This is filtered, or this is fed with water which flows through soil on top of an impermeable layer of limestone, which sits about 60 to 80 centimeters below the ground. The community deemed this spring source to be viable and that it would not run dry. So that's an assumption we're sticking to throughout our design project. And the current population is 329 residents.
We had to make quite a few design assumptions for this project due to either lack of data or just constraints. So the first is that there's 70 houses, 70 taps, and on average 4 people per house. That's coming from data from the KRV team because they were actually in Panama on the ground taking GPS. And then like Kate was saying, the emergency conditions in the dry season, we're assuming that they get water a minimum of 2 days a week. And during those 2 days a week that they do have adequate water to fill storage tanks when the water does come to the town. And like Kate was saying, there's an impermeable limestone layer, so we can't really dig out anything at the spring. It's just right below the ground. As well as in our cost estimate, we are assuming that there will be volunteer labor. So we do have a little bit of labor for skilled work, such as masonry and pipe work, but a lot of the work will be volunteered by the community members. And then finally, we do have to put a storage tank in the community. So there was no aesthetic considerations. We just were able to put the tanks wherever they needed to in order to work for the system. And also there is a current system for the municipal water that gets water to every house, and we're assuming that that is functioning as it should. We didn't get an as-built, and we're not putting in any additional water distribution. We will be tying into the existing network. So here on the left is an overview of the site. So the spring is kind of up in the woods, and will have to be pumped about 300 meters or 700 feet into the town. And that includes one little bridge crossing over a low river area, and then into the town. The storage tanks are right in the middle of the town. On the right, that is the spring. So as you notice, it's pretty cloudy. So we do have to do some clarification and just to get some of those heavier sediments out of the water as we make it potable.
So we used EPANet to determine the best location for the storage tank configuration. So one of the design constraints that we were given was that we needed a minimum of 10 PSI at all of the household taps. So this is our EPANet model shown below there, and that's showing node pressure at all of the taps. And we're assuming that this layout is representing the existing distribution system, since as we mentioned before, we didn't get an as-built. So the dark blue rectangle in the middle of the model, that's our storage tank location. And we decided to go with a gravity-fed distribution system to reduce the need for a second pump. So we had to pick a location that would provide adequate pressure and also be able to raise the storage tanks enough to provide that minimum PSI at all of the taps. And here we're showing node elevation at all of the houses. So the elevation in the community ranges from about 20 to 70 feet relative to the spring source. So we also decided to choose a relatively high location within the community so that when we raised the storage tank configuration, we didn't have to build an extremely tall tower. So we determined that we needed 24 feet from the ground to the bottom of the storage tanks to provide the correct pressure for each tap.
Getting into the design at the spring source, the design of the pump will be solar powered. So this is just a little overview. The blue lines are the spring, and then the spring box is sitting right over top of it to capture that water. And then there will be a 9-panel solar array hooked in. Panama gets a lot of sun, so we've determined this is an adequate amount of power to power this pump. And there's a little overflow trench just in case, because in the wet season, the spring can get pretty full, and it'll be all enclosed in a barbed wire fence to prevent theft and vandalism. That was something that was stressed upon us by our sponsors in the area. So we needed to account for that in all of our designs. Looking a little more just at the spring box itself, it's kind of got 3 components. So the wing walls are where the water would flow in, and it's full of crushed rock wrapped in geotextile. And so this is kind of to serve as a roughing filter, get some larger debris out before it gets into the spring box. And it also runs through some architectural perforated block to further make sure that there's no large debris in there. And then it flows into a sedimentation basin where it is able to settle out some of the larger particles. As you saw, the water was pretty turbid. It flows over a weir, that green box there, that's a weir, and so it clarifies it into the wet well where the water will be pumped from the pump house, which is located on top of the wet well. As I was saying, the pump house is located right on top of the wet well. Just for the idea, there's 2 pumps in that drawing. We do only have one that was offered as a design alternative to put 2 pumps just for redundancy and maintenance. But the pump house is going to house all the pump controls as well as the pumps and electrical components, and it will be locked to prevent vandalism and theft as well.
All right, so our design requires the use of a bridge crossing that'll get our supply line across a small river. This river sits between the spring source and the community where the storage tanks are located. The stream itself spans 36 feet bank to bank. The design that we elected to use is pretty simplistic, frequently used around Panama. This was recommended to us by Rick from Footprint Possibilities. So this design utilizes 2 tree anchors on either side of the stream, and then a steel wire is attached to both of those trees and run across the stream itself. Then 1-inch pieces of PVC pipe are cut and fed onto that steel wire, as you can see in the bottom image. Those are then attached to that wire with billing wire, just they stay in place. And our supply line is fed through those small PVC circles, and that's what runs it across the entire stream. Because this supply line is not covered by anything, we do have to use a protective paint so that it doesn't deteriorate from the UV light. We also included an alternative design that uses concrete anchors instead of trees. We're assuming based on the foliage in the area that there will be trees, but if not, the community has another option.
So the main treatment component of this system is a slow sand filter. So it's located at the top of the storage tank configuration, and it was sized to take up the entire top level of that to maximize the rate of filtration. So it consists of poured concrete housing material in a square, and it's filled with 4 grades of medium material, from fine sand at the top, then followed by fine gravel, medium gravel, and coarse gravel. There is a partition wall in the middle to support a distribution manifold, so the influent water will flow through that manifold and be dripped into the filter. That will prevent the influent water from gouging out the media bed, which could affect the filtration efficacy. And the way the sand filter works is that there's bacteria and algae in the influent water, and that grows a biological layer on the top of the sand, which then will metabolize any contaminants and effectively remove them from the water. This design also contains a metal roof on top that's removable for maintenance. And it also has a fine filter mesh fabric on top to prevent large dust or windblown debris from excessively contaminating the filter. And housed in the bottom of the media bed is a perforated under drainage manifold that consists of 2-inch perforated PVC pipes running the length of the housing bed. And that will collect the treated water, funnel it to a 4-inch PVC main drain in the middle, and that main drain will lead through the top storage tank configuration level through the chlorinator and then into the storage tanks themselves. And as I mentioned, after the water exits the sand filter, it needs to be chlorinated. This is because we are connecting to the municipal supply line. So we needed to chlorinate the water to prevent mixing raw water with the treated municipal water. So this is a picture of the chlorinator that we chose. It's an inline chlorinator, and it'll be located between the sand filter and the top of the storage tanks. It requires a chlorination tablet, and we did determine that this chlorinator is potentially excessive for this system and the amount of flow that will be going through it. So it is adjustable, but the community will need to monitor it to make sure there's not excessive chlorine, and that if there is, it'll be volatilizing out of the tank so they can monitor that chlorine level to make sure it's safe.
The final component of our design is our elevated storage tower that houses our sand filter and our 5 PVC storage tanks. This is a 56-foot tall concrete structure. So as we said earlier, aesthetics is not really a consideration. This will be an eyesore in the middle of the community, unfortunately. But it's what allows us to give our gravity-fed system, which ultimately cuts down on our cost. So as I said, that we've got 5 storage tanks that we are going to provide and spec out right off the bat, but there is space within this level to add an additional 6th storage tank down the line if the community has the funding and decides that it's needed with community growth and whatnot. All of the storage tanks are connected in series through a piping network, with the final tank ultimately tying into the community's distribution network. As theft and vandalism, I know we've hit this already, but it is a huge concern. And with this storage tower being right in the middle of the community, it's even more imperative for this to be contained. So we've got a chain link fence with barbed wire, again, to deter vandalism and theft. So as this was a value engineering assessment, we kind of just needed to look at KRV's initial design and see how our design fell in with theirs and ultimately cut down on cost. So the combination of our spring box and pump house was a big way to decrease the ultimate footprint around the spring area, which cut down on the quantity of materials and the excavation and clearing needed of the area. KRV initially had their spring box and pump house not on top of each other, ultimately taking up more space and requiring more materials. We simplified our water crossing bridge. As you saw, it's basically just PVC and a steel wire or steel cable, I'm sorry. They had a much more complex design requiring concrete foundations, columns and all of that stuff. So that decreased cost there. Our elevated storage tanks on our storage tower allowed us to not need a second pump or pump house right in the community. So the gravity fed system helped a lot with that. Again, tying into the existing network, that is something that KRV did not do. They created their own distribution network because they did not include a flow sand filtration system. They could not combine the water from the municipal line with the water that they were getting from the spring source. As we were able to do that, we are able to just tie right into the existing network, negating the need for additional cost there. Once again, we just wanted to hit that we hit all of the design components that KRV did with the addition of a slow sand filtration system, which provides an affordable way to treat the water from the spring source going into the community taps. Here's our cost estimate broken down by our major bid packages. As you can see, a lot of the structures are our most expensive components, as that requires a lot of expensive materials. Our cost estimate is based on United States pricing from RS Means. This is what KRV used, and in order to create an accurate comparison, we wanted to continue with that. Ultimately, our final estimated price came out at about $66,865, which does exceed our $40,000 budget, but we are confident in our design that we did the minimum, or we provided the most simplistic design while providing a design that is safe and effective for what the community needs. Where our estimated project schedule is to be completed in about 11 months. While this design is simplistic, our assumption is that community labor will be provided, but on a volunteer basis, but that is never guaranteed. We assumed that we would have about a crew of about 4 individuals working at any given time, but that can be unskilled labor that extends the period of time for pieces of construction to occur. We have our Gantt chart here. It is very small to see, and I don't expect you to try to read any of those tasks, but it's really just showing that none of these tasks are going to be occurring simultaneously. They'll all be occurring one after the other. Again, going back to the lack of certainty of labor, we didn't want to bank on anything being able to happen at the same time. If it is, that's fantastic, and that'll ultimately cut down on our project schedule. But again, we did not want to count on that. So our next steps is gaining permitting from governing bodies that are applicable to this design. We are assuming that the existing distribution network is okay to tie into, but that will need to be inspected to make sure that that is okay. With us and KRV both exceeding that $40,000 budget, we feel that it verifies that further funding will be needed in order to meet the needs of the community. And once again, we will need community volunteers in order to provide labor to make sure that this can come to fruition. Thank you. Are there any questions?
Sorry, you've mentioned solar powered pumping system or design at one point, but I didn't see like in the cost of what that encompasses that. Like, I didn't know if this was all gravity fed or you had to pump it up.
So from the spring source, we do have to pump it into the town, and it's included in that pump house cost, all the electrical components and the solar panels would be, yeah, part of the cost estimate. So that's,
So the spring is at a lower elevation.
the spring is at a lower elevation, yeah. So the previous design, they just didn't have that big storage tower, and they had another pump system to get it to the houses, but we eliminated that one, but we couldn't, there's no way to eliminate the other one.
Right, I'm gonna ask my question, you can ask your both answers. So my question, so Isabel, I suppose you get first right of refusal on my question. So we talked about the layer at the top of the sand filter. That's really important in terms of that filter removing organic matter. But we have a name we like to use to describe that layer. Do you know what that thing is?
I looked it up. It was called the schmutz deck.
Yes, I'm so glad. I wanted to hear that. That's just a fun word. It's one of those that environmental engineers. Okay, I'm happy.
Other questions? Students, please ask questions too. You guys ask each other questions.
What was the most challenging part of the university?
Probably the fact that we are working with a system that is so far away that we often didn't really know exactly how it looked. That kind of often was hard to wrap your brain around what she was doing, given we'd never really been there. And the other team had the benefit of boots on the ground. They were there for spent 10 days there. And so I think that was definitely a challenge.
And I think too, adding on to that, a lot of the documentation we got from Footprint Possibilities was in Spanish, which just added one more hurdle for the team.
Yeah. Sadly, none of us speak Spanish.
I know we had a lot of consideration and stuff at the structure. Do you have any particular happening with the bridge connection? I feel like that's exposed.
That's something that would definitely have to be considered, because the bridge crossing, depending on what anchor is used, if it's a tree, there would likely have to be fencing put around the tree itself, but it would be hard to cover the entire stream crossing all the way. But I definitely think the anchor points could use fencing.
I do have that question. So for your spring rocks, you had the sediment, basically created a space for sedimentation. Your water was quite cloudy, then how are you going to get the solids out that do settle there?
Yeah, it'll have to be cleaned out. I believe it's in our operation. I mean, it's like monthly or something, but there are access hatches to get into each section of that spring box. So if someone have to go in and actually clean it out, yeah. But it is, yeah, it's not like a solid bottom on that part. So the only part that has a solid bottom would be the wet well. So it is kind of a natural bottom. It will build up, but not as bad as if it was like a concrete base.
It's time for one or two more questions.
So I was wondering if you looked at other alternatives to that big structure, 56 footer, because that's humongous. You know, and it's, I need to do some geotechnical investigations to design the footing correctly. or else it's gonna be a hazard. 56 feet, this room is 20 feet high, right there, it's 3 times higher. So what was it that sort of led to that need of having such a tall, big structure? What alternatives did we have?
So the initial design that we looked at, that the previous team had, was just a concrete slab with a storage tank right sitting on top of it, basically at ground elevation within the community. That did require an additional booster pump and pump house within the community to get the water to all of the taps. That was ultimately a lot more expensive than building an eyesore of a 56-foot tall tower that would then be gravity fed. We did play around with different locations within the community to see if there was a different spot in which we could make the towers any smaller. We chose the elevation within the community that worked best for us and allowed the 10 PSI for each of the taps. Unfortunately, it's still 56 feet tall.
It is worth noting that we were assured that the community members, that there's people in the area that are able to build a tower like that, and there are towers of that configuration and other places. So they really just want to get away from too many pumps, too many things that could break. Really wanted the gravity filter, and they assured us that they would be able to make a storage tower like that. There are others elsewhere. But you're right, it is large.
You did have an alternative design that you didn't mention.
Yeah, so I guess the other alternative design would just have been the sand filtration at the spring box source. So you would have had to add another pump to pump it to the top of the sand filter, then run down and then pump it to the storage tanks. And in that case, that tower would just have to be the first level of the tower. You could get rid of the sand filtration there and have it at the spring source. But then again, that's 2 pumps. And so that's why it ended up being a design alternative.
Okay, well, thank you.
Yeah, I know. That's
Just add another account and sign everybody out. Not seeing any questions on the chat. Yeah, just leave it. Okay. So just add one.